we now give the proof of the approximation theorem. So what we will do is we will first make a reduction that should have been clear to the reader once during our discussion of the Bernstein polynomials. So exercise show that it suffices to prove the approximation theorem for the interval AB being nothing but close 0, 1. Okay, so you don't need to establish it for an arbitrary interval. You can consider the special case close interval 0, 1, and that's enough. Okay, so once this exercise is done, we will focus on close 0, 1, and we will use the Bernstein polynomials. Okay, so central claim is that these B and F's converge to F uniformly on close 0, 1. That's what we have to show. Okay, so now to do this, as I had mentioned before, we are going to analyze points in two separate set of points. What we are going to do is we will analyze points that are close to k by n and points that are far away. That's somewhat vague remark, but that's what we are going to do. So let's begin the proof. So fix x in close interval 0, 1 and 0 less than delta less than 1. Okay, now we want to analyze the summation k equals 0 to n bkn of x f of k by n. This is what Bn of f is. Okay, so to analyze this, what we will do is we will just focus on the sum of the Bernstein polynomials. First, what we will do is we will consider summation over k by n minus x is greater than or equal to delta b kn of x. Okay, so note we have fixed the x. We want to analyze summation bkn of x fk by n. What we are going to first do is we are going to consider the sum bkn of x where k by n is far away from x. Okay, note x is fixed. Okay, now this is certainly, of course I'm using a shortcut here by this is to denote that we are only summing up over those cases for which k by n minus x modulus is greater than or equal to delta. Now this is of course going to be less than or equal to summation mod k by n minus x greater than or equal to delta 1 by delta squared k by n minus x the whole squared b k minus n x. Okay, so what we have essentially done is we have multiplied by k by n minus x the whole squared, which we know is greater than or equal to delta squared, and we are dividing by delta squared. So in essence we are multiplying each term b k n x by a quantity that is greater than or equal to 1. So this is certainly going to be less than or equal to. Okay, so now we have to estimate. So this is a trick. So this is essentially just a trick. So now we want to estimate summation k by n minus x the whole squared bkn of x. Okay, this is what we have to do. So look at summation k equals 0 to n k minus nx the whole squared pknx. Look at this quantity instead. Okay, now from one of the identities involving the Bernstein polynomials that was left as an exercise to you last time, we can simplify this in a by using those properties we can greatly simplify this. What happens is this is nothing but summation k equals 0 to n k into k minus 1 minus 2nx minus 1k plus n squared x squared, okay, this whole thing times b k n x. Okay, so please check this. Please check that you get k into k minus 1 minus 2nx minus 1 k plus n squared x squared times b k n x once you expand this out. And this, by the various identities that we have established involving the Bernstein polynomials, this is nothing but n into n minus 1 x squared minus 2nx minus 1 nx plus n squared x squared. Okay, fine. So you can check that this is nothing but nx into 1 minus x once you do the basic arithmetic, and this is going to be less than or equal to 1 by 4n. How did we get this last step? That seems a bit weird. Well, the last step involves this basic property that x into 1 minus x is less than or equal to 1 by 4 when x is in close 0, 1. Do you know why this is true? Can you prove this? You can use calculus to prove it. You can also prove it by elementary observations. I urge you to try it in two different ways. One using calculus and one using just elementary basic stuff. Okay, so now that we have this equation that nx into 1 minus x is less than or equal to 1 by 4n, ultimately what we have is the term we started out with. Summation k equals 0 to n k minus nx the whole squared b k nx is less than or equal to 1 by 4n. What we do is we divide both sides. As expected, we divide both sides of left extreme and right extreme, left extreme and right extreme by n squared. Okay, once we do that, we get summation k equals 0 to n k by n minus x the whole squared b k n x is less than or equal to 1 by 4n. Okay, so what have we managed to achieve? Well, what we have done is we fixed delta and we managed to show that if k by n minus x the whole squared is greater than or equal to delta square, in other words, if k by n minus x is greater than or equal to delta, then this summation k equals 0 to n k by n minus x the whole squared b k n x is less than or equal to 1 by 4n. Now what are we going to do with this? Well, we know that f is going to be bounded. Why? Because it is a continuous function on a closed interval. So f is going to be bounded. Okay, suppose mod f of x is less than or equal to m for all x in 0, 1. Okay, so choose a sort of an upper bound for this function capital M. Then what the final quantity we are really interested in is f of x minus bn of f of x. This is what we are interested in. This is going to be nothing but summation f of x minus summation mod k by n. So I shouldn't really write equal to. I should write, we are first analyzing those terms. We are analyzing those terms for which k by n minus x is greater than or equal to delta. So we are essentially analyzing the parts where k by n minus x modulus is greater than or equal to delta separately. So f of k by n b kn of x, which we already know is going to be less than or equal to summation mod k by n minus x greater than or equal to delta mod f of x minus f of k by n times b kn of x. Okay, now how did we pull this trick? Well, we pulled this trick because summation b k by n x is in fact equal to 1. This we already know. So what we have essentially done to establish this from the previous step is this f of x, we have written as f of x summation b k n x, and we have taken this f of x inside, so we have written this as summation f of x b k n x. So this is what we did to the first term. Okay, from that this should become apparent how we got mod f of x minus f k by n b k n x. Okay, now combined with what we have established regarding k by n minus x the whole squared b k n x is less than or equal to 1 by 4, and combining that, what we get is this quantity is going to be less than 2m times 4 delta squared n, which is nothing but m by 2 delta squared n. Okay, so kindly check this. Okay, so what we have now established is that when x is far away from k by n, then f of x and b and f of x are close, right? All we have to do to make bn of f close to f of x now is to make this small n large. If you make small n large, then we will get that bn f x and f of x are very close to each other. Now we have to deal with those points for which x is close to k by n. Okay, so what we have essentially done is we are splitting the sum b k and f of x into two parts, those where which k by n is close to x and those where k by n is far away from x. So what we do is fix epsilon greater than 0, and now we are going to choose delta appropriately to get what we need, and choose delta greater than 0 such that if y comma z are in close 0 1 with mod y minus z less than delta, then mod f of y minus f of z is less than epsilon. We can do this because f is uniformly continuous. Because f is uniformly continuous, I can find a delta that works universally for all points y comma z in the closed interval 0 1. Note that this second part, analyzing where x is close to k by n, we won't really require any of the properties of the Bernstein polynomials. Just the fact that f is uniformly continuous is enough to finish the proof. Okay, so now we need to again analyze mod f of x minus summation k by n minus x is less than delta f of k by n b k by n x. Okay, this is less than or equal to summation mod k by n minus x less than delta, again mod f of x minus f k by n b k n x. Okay, by the exact same argument that I had highlighted when we had a similar inequality in the previous part. Okay, but we are summing up over those k by n's where mod k by n is less, mod k by n minus x is less than delta, and by uniform continuity this is just going to be less than epsilon times 1. Okay, which is epsilon. Okay, so now what we do is we choose, so we have to combine both parts. We choose delta so that this equation is satisfied, so that star is satisfied, That is, those points where k by n is close to delta can be dealt with. Now for this choice of delta, we choose n so large that m by 2 delta squared n, which was nothing but the quantity that we got when we analyzed the previous term, is also less than epsilon. Net upshot is we will get that Bn of f x minus f of x is less than 2 epsilon for all x in close 0, 1. Okay, this will be true when n is suitably large. And this concludes the proof. So the proof of the Weierstrass approximation theorem that we have given ultimately relies on the uniform continuity of the function f and the basic properties of the Bernstein polynomials. We analyze those points x which are close to some k by n, and for analyzing this just uniform continuity is enough. For those points for which k by n minus x is somewhat far away, we just use the basic properties of the Bernstein polynomials, and combining both we get the proof. This is a course on real analysis, and you have just watched the module on the proof of the Weierstrass approximation theorem.